Good afternoon, everyone. Welcome to today's talk on how to performance tune Spark applications in large clusters. Before we start, I want to set the context of what to expect from this talk. So this talk is not about how to set Spark configuration so that you can start running your Spark application. So most of the Spark configurations, you can find it online. So this talk is more about when we built Marmari at Uber, which is a generic ingestion system to ingest data from any source to any sink. We did something differently than what is readily available when you Google outside. So that's pretty much what we will be talking about in this presentation. I have divided the presentation into 4 different improvements, and let's look at them. So this is brief introduction about who am I. So I'm currently a software engineer at Netflix. Before that, I was a software engineer at Uber, where I architected and authored Marmari. Prior to that, I worked with a company called Hedwig, which is software-defined storage company, where I architected object storage and their NFS solutions. This is agenda for today. I'll briefly talk about JVM Profiler, Hadoop Profiler, Spark Listener, AutoTune, and then the rest of the talk, I'll focus more on 4 different improvements, primarily storage, CPU runtime, efficiency, and memory improvements. So why profiling Spark job is very important, and why is it very challenging? So profiling a simple standalone Java application is a very simple problem, because you have the application running all the time. So you can connect a remote debugger, or you can even use different profiling techniques to profile individual API or certain class code paths. It becomes very challenging with Spark, primarily because, first of all, it is running on thousands of executors. And the second is, if you have seen a Spark application running in production, then you know that the Spark job is divided into multiple Spark stages. And every Spark stage is executing different code paths. What it means is, like, when you want to know, like, okay, if my Spark job is running fine or there is a room for improvement, I don't know, because since it's spread across so many Spark stages, I don't know which Spark stages should I go after, and there is a room for improvement. And that's when a Spark team at Uber built JVM Profiler, so that all the Spark developers can debug Spark applications and performance tune that. This JVM Profiler is available online. It's an open source, and the team has already presented it at previous Spark Summit. So if you are interested, please go and check out their video. At a high level, what Hadoop Profiler is, it's basically a Java agent. So when you are defining a Spark conf, in the extra arguments, you will provide some configurations which is listed on their website. And once you submit a Spark job, whenever executor comes up, it comes up with this Java agent attached. This Java agent lets you do some profiling. First is CPU memory. So when we say memory, it also tells you like the split of the memory. So let's say you are consuming some XGB of memory for your heap, some remaining XGB of memory for your off-heap. Off-heap also, it will give you further more information. Like let's say if you are using direct byte buffers, or if you are using memory map buffers, then it gives you pretty detailed information about the memory. This is the specific piece which we used when we were figuring out memory usage for Marmari jobs, which I'll be talking about later in this presentation. The second thing is the method duration profiling. So let's say you have some API calls which you are making to name node or data node, and you want to profile them. Hadoop Profiler is the way to do it. And the third thing is method arguments profiling. So let's say if you are making some remote API calls and you are passing some arguments, Hadoop Profiler lets you profile them as well. Once the information is collected in the Java agent, it needs a way to report them. So the default reporters are Kafka and InfluxDB. At Uber, we use Kafka, but if you want to add your own reporter, it's open source, so feel free to go and add your own. Spark Listener, we are using at Uber for different reasons. One use case is to detect if there is a node which is slow because there is, let's say, a disk issue or a network issue. So we want to identify which task is running on that executor and probably kill that task or probably blacklist that executor. So that's one use case. The second use case is to do the task analysis. So let's say your Spark job ran, but now you want to know what happened, like which task was running on which executor, how much time it took, was there a way I can change the Spark scheduling logic so that I can also I can run this task on somewhere else. So that all information you can capture using Spark Listener. So let me set the context for what we did as a part of the AutoTune. So typically what happens is data science team has a Spark conf template, and that is what they use for running all their Hive on Spark queries. So what we saw as a typical pattern at Uber is usually they will have like a default Spark configuration. So when I say default configuration, I'm talking about memory and number of executors they are using to run the query. It runs fine till they start accessing bigger Hive tables, and that's when it starts breaking. So usually they tune that Spark configuration by adding more number of executors or adding more memory to it. The problem is once that bigger table query starts running, they check in that configuration into their central repository. The downside of that is it now gets used in all Hive on Spark queries which they are running against our production Hive cluster. So let's say previously they were using only 500 executors to run all their Hive queries. Now suddenly they need 2,000 or 2,500 executors. The problem which we noticed is they actually don't need those many executors to run all those queries. Only a couple of queries need those many executors. So in order to save money for company, what we did is we basically looked at the historical pattern of those queries and analyzed that, okay, when they specify, let's say 500 executors with 16 GB memory, do they really end up using that? If not, then there is a room for improvement. So looking at the historical pattern, we adjusted the number of executors and memory to see if the query finishes. If not, we will always fall back to the configuration provided by them. What this helped us is, this helped us a lot by reducing the yarn queue usage footprint and thereby saving money for Uber. So all these Spark improvements we did when we were building Marmare. So Marmare is an open source project. It was open sourced in Spark in September 2018. I've added a GitHub link. So if you are interested, please go and check it out. There's also a link to the blog post. So please check out the blog post. This is a high-level architecture of Marmare. I'm not going in too much detail about it. There are many presentations we have given outside where we have talked about it in detail. The only thing I would like to highlight here is the entire Marmare ingestion framework is supposed to ingest data from any source to any sink, and it is built on top of Spark. So we use Spark as our execution framework. Now let's talk about Spark job improvements. First, I'll be talking about storage improvements. Entire analytical data at Uber is stored in Parquet format. Parquet, as you all know, is a columnar data format. What that means is, let's say you have 100 rows, which you are trying to store in the Parquet, and let's say every row has 4 columns. Then the way the data is stored in Parquet is, for all 100 rows, column 1 data will be written first, followed by column 2's data for all 100 rows, then column 3, and then column 4. So we looked at the different types of compression we get when we write the data to Parquet. There are 2 types of compressions you can get. One is columnar compression, and the other one is snappy compression. Snappy or any compression type you have chosen. It could be gzip, it could be Brotli, or it could be something else. What we observed is, since it's a columnar storage format, you get much more benefit if you take advantage of the columnar compression rather than using different compression types. Let's look at the example. So here we are trying to store user information in the Parquet. And as you can see, we have a total 5 columns. User ID is a unique identifier. So that's never going to be unique. Now, let's say if we are sorting the records by user ID and storing that in Parquet, you can see that in the upper table, all 5 columns do not have anything in common. So if you are writing this into Parquet, you will not get any columnar compression. All you will get is the compression, which is which let's say if you're using Snappy or gzip, so let's say 5 or 10% of compression is what you will get. But if you restructure this data, as I have shown it in the below table, let's say if you sort this rows by city or state, then what will happen is all users who are part of the same city are together. Now, what will happen is, let's say if you want to store the bottom table into a Parquet, then column 3 and column 4 have identical values. So in the upper table, if you are trying to store in Parquet, you would have ended up storing roughly about 10 values, 5 for city and 5 for state. But if you are storing it in a sorted format, since they are identical, you will only store two: one for city, which is Atlanta city, and one for state, which is Georgia. So here you can see that you will get a lot of compression by sorting the records by city and state. So one thing I would like to highlight here is, so whenever you want to decide what sorting criteria you should be using, take a look at your cardinality of individual columns. So it has worked best for us, which is if you know the cardinality of the columns, sort the records with increasing cardinality. That's where you most likely are going to get better compression, but always try different combinations, because you can have a column which has, let's say, a textual data, and it's a longer length. So it's taking more storage space. So if you sort with that as against sorting by a byte, you'll most likely be getting better compression. Now let's talk about CPU and runtime. So in this section, we actually did a lot of improvements. So let's first talk about Spark accumulators. We can see that Spark accumulators are used heavily. So if you are going to Spark UI, and you see all the metrics which are populated there, behind the scene, they are all long accumulators. So traditionally, that's what a lot of people are using in their Spark code. But along with Spark long accumulator, Spark framework provides something called as accumulator v2, which you can see on the right side. This accumulator v2 lets you define your own custom accumulators, and that can be a very powerful tool. This is an example of how you can actually use accumulator to solve a real business use case, at the same time reduce runtime and as well as save some resources. So the use case we are trying to solve is, let's say you have a set of rider records and you want to deduplicate those records. While doing deduplication, you want to figure out how many duplicates you see per state. So that's the goal. So let's start. I'm right now focusing on the left section of the slide. So first, we are trying to read the records from Parquet. Then before deduplication, we will try to find out the records per state. I'm talking about a very naive way. Then we will try to dedupe the records, which is step 3. Step 4, after deduplication, we want to find out how many records we have per state. Step 5, the deduplicated records, we will write it to HDFS. Step 6, since we have 2 counts, one after deduplication and one before deduplication. So if you take a diff, we'll know how many duplicates we have per state. So let's say if you run this Spark job, you'll see that there are 5 Spark stage, and 3 of them are coming from count by key, which is not required. And it's definitely something we can improve upon. So let's look at the right side now. So what we have done is we have defined a custom accumulator called a writes per state accumulator. What it takes is basically a map of string comma long. So string here is the state ID, and long is basically number of writes per state. What we will do is we will define 2 such accumulators, one for writes before state and one for writes before dedupe, and one for writes per state after dedupe. What we are doing here is, if you look at the argument which is passed to dedupe function in line 3, we are just chaining a map operation. And as you know, map is not going to, it's not a Spark action, it's a lazily evaluated code. So you are just chaining some extra functions to be executed for every record whenever this DAG gets executed. So we are adding such one map function, and we are saying that for every record, increment the counter based on its state ID. After deduplication is done, we are chaining one more map operation where we are doing where we are trying to increment the count for writes per state after dedupe accumulator. Finally, we are sending that for writing to HDFS. So here in this entire Spark DAG, write to HDFS is the only action. Once that gets executed and has finished, on the driver, you will have basically 2 accumulators populated with respective counts. So once the action has finished, you can take the diff, and you will know the how many writes have duplicates per state. The good thing is if you run this if you run this code, you will only have 2 Spark stages, and it will do exactly same what it did on the left side. So the good thing is like you will be able to save a large number of executors runtime, and thereby you will be able to save cost. Let's look at the other example. So we had an ingestion system which was ingesting data from Kafka to Hadoop. I'm talking about a case where we have a topic which has 256 partitions, and just for this hypothetical use case, it has 3 billion messages per run. The problem is Kafka, we were using Spark Streaming Library to read from Kafka, and Spark Streaming Library has an inherent disadvantage, which is it tries to pin Kafka partition to a specific executor. What that means is, let's say you want to read from same Kafka partition from 2 executors, it doesn't allow you to do that. It basically tries to serialize the operations when you are trying to read from a same Kafka partition. The problem is we have lots of operations we want to do on this data which we have read from Kafka before writing it to HDFS, like sorting the records, grouping it, group by, order by, some n number of operations, right? So for that, we can't be using 256 executors. We want to use more executors. So typically, like this is what is done in industry is you read from Kafka and then you shuffle. So you basically have a repartition stage right after that, and you send the data to as many executors as you have, and then you get more parallelism. The problem with this approach is, as you can see, in order to do repartition, what you are basically doing is you are doing a shuffle write, which is around 1.3 terabytes, and it is followed by a remote shuffle read, which is around 1.3 terabytes. So there are 2 problems. One, definitely CPU cycles are wasted in doing a shuffle write and shuffle read. And the second problem is that you are also wearing out disk. So if you do this frequently, then you are basically trying to reduce the lifetime of disk. So you have to replace the disk very frequently. So this was a problem, and what we did basically is we tried to remove this restriction from Spark Streaming Library, and we basically split one Kafka partition into 32 virtual partitions. We made this configurable, so you can define how many virtual partitions you want to create for every Kafka partition. But what that let us do is we can now read from more than one executor same Kafka partition. So think of virtual partition as one Kafka partition, let's say we were reading earlier 400 messages. Now what we are doing is we are saying one virtual partition is read from Kafka partition 1, offset 0 to 100. Second virtual partition will try to read it from 101 to 200, and so on and so forth. So in order to achieve that, this is what we did. So if you look at the Spark Streaming Library code, then there is something called as Kafka RDD, and in that there is a get preferred locations, and that's how they actually pin Kafka partition to executor. We sort of override that feature. So another way to improve Spark performance is by using cryoserialization. If you have not been using it, I'll highly recommend it. There are lots of advantages with Cryo. One is it has lesser memory footprint than Java Serializer. It's faster. It supports custom serializer. There is one issue though with Cryo, which we fixed in our internal Spark build. It's not yet open sourced, but very soon we will do it, which is when you are setting some Cryo specific configurations on Spark driver, they today are not propagated to all the executors. What that means is like if you look at the Spark UI, you will see that, oh, I have set all these Cryo configurations, but they are not actually getting used. This is like something we observed when we were debugging Cryo serialization streams when we were performance tuning Marmari. So there are some things I have highlighted here. One is, let's say if you are using a Spark with Avro generic record, then it's recommended that you register your Avro schemas because that helps you reduce your Cryo serialization stream size. I'll be talking about that in the next slide. And let's say if you are using some custom classes, then it's highly recommended that you register those classes using Spark Cryo classes to register. And if you're not sure what classes I should be registering, just turn on the registration required configuration. It will in the logs, it will start spitting out, okay, this is the class I'm not able to find. So that way, basically, you can do some n iterations and add all the classes into the config. So now let's look at the Cryo serialization stream without schema added into the config and with schema added into the config. So on the left side, we have not added required schemas into the config. So this is how the cryo serialization stream will look like. So what Spark does, what cryo does is, it will write schema for every record written to the cryo serialization stream. So let's say you are writing that to disk or sending it over network. This is how your serialization stream will be. So if your schemas are big, which is most likely case for us, then your record size will be around 4,228 bytes. But let's say if you register the schema, then you are just writing a schema identifier, which is 4 bytes. And let's say your data remains the same, 128 bytes. So then you're basically reducing your record size from 4,000 bytes to around 132 bytes. So this is like a huge saving you can get. And this actually helps in disk and network IO. Another improvement which we did was by restructuring our payload. So let's look at the left-hand side, which is we have a typical Spark payload, which has some custom metadata information, and then there is some extra payload. Here, line 6 is that custom payload, which is basically a map which has a string as a key and value as a generic record. The reason I put it here is because let's say this has, let's say, 100 to 1,000 keys, okay? And this Spark payload is used in multiple Spark operations. So we have we are reading it from some place, then we are doing sort by, we are doing count, we are doing group by, order by, bunch of operations we are doing. And finally, we need this data when we are writing it to HDFS. I'm just making up this use case. The problem with this kind of a payload is whenever you use Spark payload in any of your Spark operation, Spark has to deserialize the entire Java class. So let's say this map has 1,000 entries, and let's say this generic record has a super complex schema. What will happen is Spark will spend a lot of CPU cycles in serializing and deserializing this object, which is not required. Let's say if you are just in this use case, if you are just looking at sorting key, then it makes more sense to serialize this map, which is what I have done on the right side. So let's say if you have something like this, store it internally in a serialized format. So you can just add a byte array. The advantage is whenever this Spark payload is deserialized by Spark, all it has to do is read binary data from disk and put it in this. So the number of CPU cycles spent for this are way too less than spent on the left side. Another improvement which we did was by parallelizing Spark iterator. So let's look at an example. So I've added a very simple example where we have some map partitions function, which provides you an iterator on records. And we are just doing while I has next, parquetwriter.write. And once I run out of records, then basically I'm going to call parquetwriter.close. So this is a simple way of writing records to Parquet. And now let's look at what happens as a part of this operation. Okay, I'm focusing on the left side. So the color coding is this way. Orange means everything happens in Spark land, and green means everything happens in user land. So what happens is whenever you are performing i.hasNext, Spark has to figure out if there is any record or not. So it is going to hit the disk, it will read the stream, it will see, okay, I have a new record, it will return true. So whenever you say i.next, it will basically return you the next record. So once you get the record, you will give it to columnar Parquet writer. Once your row group is filled, Parquet writer will do columnar compression, write it to underlying output stream, and data will be returned to HDFS. So far, so good. The problem we were seeing is since we were writing 1 GB file, this whole operation was taking 45-ish minutes. So that was not expected. We wanted this to run faster. So what we did is we basically split the responsibilities. So we let the Spark thread read from disk and populate into an internal shared memory buffer. And we spawned a new thread which can read from this shared buffer and do the Parquet write operation. The advantage we got with that is since we have now 2 threads and they are sharing a buffer, we can read very fast from Spark and also finish this whole operation quite fast. So we were able to reduce the runtime from 45 to 25 minutes by just doing this optimization. So if you have a use case, something like this, please think about this. Now I'll be talking about the efficiency improvements. This is a very simple use case or a very simple Spark code I've written, which I'm sure will never run in production. But what I'm trying to highlight here is, let's say we have a Java Spark context and we are reading from Kafka. We have, let's say, topic 1, and then we write it to HDFS, right? Now, if we try to see what happens when we run this code, this is how something like this is what you will see. So the vertical axis is basically executor IDs, and horizontal axis denotes time. And in between that, we have a lot of red pointers. So those vertical lines basically mean stage boundaries. Now you can see that there are a lot of places where only you see one horizontal line. That horizontal line indicates that there is only one or maybe two Spark tasks which are running, and every other executor is sitting idle. So a lot of white space here indicates that there is a lot of time spent as a part of running this Spark job where executors were sitting idle. So if you now see the efficiency of this job, the efficiency of this job is going to be very, very low. And that's a very big problem, because finally, when you're running an ingestion system, all you look at is what is the dollar value you're going to spend when you're moving 1 GB or 1 TB of data from source system to sync system. Now, that dollar value is going to be very high for a system like this, because you're wasting a lot of resources and there is a room for improvement. So what we did is, we, instead of launching ingestion for one Kafka topic in one Spark job, we clubbed a lot of Kafka topics together. So what we did is, we basically launched, at Uber, we launched 32, but take a look at your own run, take a look at your own Spark DAG and you can decide your own configuration. But 32 worked very well for us. Now you can see that there is hardly any white space here. You will only see white color right at the end as a vertical line, but that's expected because when you are almost finishing the Spark job, there is pretty much nothing left. And that's why there are some executors who are going to be idle, which is okay. But if you look at the left half, this is completely filled. All these colors means that the Spark executors are working on some task or the other. So finally, I'll talk about memory improvements. Here, I'm primarily focusing on off-heap improvements, which we had to do. So if you remember, like in the beginning of my presentation, I was talking about JVM Profiler, and it helped us in memory profiling our jobs. This is what it helped us with. So what was happening is, our jobs were running with 7 GB of memory, and they were running fine. So our job was running for, let's say, 30 minutes. Up to 25 minutes, everything was fine, and suddenly we were seeing a couple of executors getting killed. When we looked at the driver logs, this is what we see. This is what we saw: container killed by Yarn for exceeding memory limits. And we were not sure what's going on, because we were not using extra memory. We were not doing any off-heap memory operation. So we were not sure what's going on. So JVM Profiler helped here. So what was happening is, we use persist very heavily in Marmara. So we cache lots of stuff so that we don't recompute operations. What happens is, Spark, let's say you have executor 2, and which needs data from previous stage. It will, and if that previous stage task did not run on the same executor, it will quit. It will ask for that data from some another executor. Now, when it does that, what Spark was doing till Spark 2.1 version is, it used to memory map the entire file. So let's say you have some RDD blocks which are 1 GB or 2 GB in size. Then let's say suddenly some external executors request those RDD blocks, then Spark will simply start memory mapping those files. And what will happen is, that will simply jump up your physical memory usage. And that's why Yarn, which is monitoring the physical memory usage for every processor, will go ahead and kill it. This is definitely not something what we wanted. So we had some ideas in mind of how we can improve it. So we were thinking about doing a rolling buffer, where instead of memory mapping the entire file, we could do like some 4 MB buffers and keep rolling, so that we reduce the physical memory usage. But parallelly, we also had an ongoing task of moving from Spark 2.1 to 2.4. So the good thing is, like, if you have switched to Spark 2.4, you will not see this problem. The reason is because in Spark 2.4, they have migrated from using this memory map process to using file regions. They did that for some different reason, but actually this solved this problem as well. So if you are hitting this issue and you are on Spark 2.1, I'll highly recommend just move to Spark 2.4. That can save you a lot of memory and a lot of money for your company. If you want to fix it for 2.1, yeah, let's talk. That's all I have for today. We are hiring. If you are interested and you want to work on interesting problems, please reach out. Thank you.